Let's look at what is stress, strain, and Young modulus. Now, assuming you have a piece of material here with original length L, you can actually use compressive forces to compress it by a small distance E, or you can apply a tensile force to cross a small extension E. So we can actually define the stress, strain, and Young modulus from these two diagrams. So stress is defined as force acting normally per unit cross-sectional area. So we will take the force and divide it by this cross-sectional area. And it can also be used for this case. You can also take the force divided by the cross-sectional area. So the unit for stress will be similar to pressure, because if you remember, the formula for pressure is also force divided by area, but there's a small difference. Here we add in the word cross-sectional area, so it's force acting normally per unit cross-sectional area. But the units will be the same in the sense that you can use Newton per meter squared or Pascal. And next one, we talk about what is strain. So strain is defined as ratio of change in length to the original length. So meaning to say, if we can take the compression amount E or the extension amount E and divide by the original length L, that would give you the value of your strain. But strain, because the unit of change in length is let's say meters, and original length is also meters, so you will notice they will end up with no unit. And lastly, what is Young modulus? So Young modulus is defined as the ratio of stress to strain. So that means we take this stress value and divide by this strain value. Now, since strain has no unit but stress has this unit, so when you take stress and divide by strain, so the unit of Young modulus will follow the unit of stress, which is Pascal. Okay, so we can use Pascal. Now, what is the significance of Young modulus? Young modulus is actually an indication of stiffness. So the bigger the Young modulus, the bigger the stiffness. Give me an example. Okay, now let's combine the formulas together. So remember, we said Young modulus is ratio of stress to strain. So we take the stress formula and divide it by the strain formula. And then what we do is we make the extension as a subject. So you'll notice that once we have this formula, we will notice that the bigger your Young modulus, the smaller your change in length. So it's harder to change its shape or size. So remember, when I told you what is stiffness, so stiffness is actually resistance to changes to its shape and size. So the bigger the Young modulus, the stiffer the material, so it's harder to change its length. Now, what other things can affect the extension? Of course, using a bigger force or a thinner wire. So your original length L, the bigger it is, the higher the extension, which we will be using this concept in the next part when we discuss the experiment to determine Young modulus. We will tend to always use a thinner wire to produce a larger extension, right? And then lastly, we will use wires with smaller Young modulus if you want a greater change in length. So some people ask me, what is the difference between Young modulus and spring constant or force constant? Okay, now remember we said that spring constant is only for springs, whereas force constant can be used for wires. So let's say you have a wire and they gave you both the force constant K and also the Young modulus. Now, since both also represent stiffness, so what is the difference between them? Now, always remember Young modulus is a constant that depends only on the type of the material. So whatever the dimensions of your material, means whatever the length of the cross-sectional area, the Young modulus would remain the same as long as you're using the same material. But force constant here is a variable in the sense that if you use a longer wire, then your K will be smaller because your extension will be longer. So even though K does represent your stiffness of your wire, but it is a variable, so it will not be the same once you change the dimensions. The next thing we are going to talk about is the experiment to determine Young modulus. Now, the experiment to determine Young modulus is actually required in your syllabus. So you have to know the apparatus and how to set them up, and also how to collect your readings, and also to analyze your data to find the Young modulus. So now to determine the Young modulus, there's an easy way and there's a difficult, more complex way. But of course, the difficult, more complex way will be more accurate. Now, the easy way that many students actually use is by using the formula E equals to FL over AX. So what they will do is they will just use a single wire, all right, a single wire, and they will just apply a load here and find out what is the force, and then they will measure the original length L, okay. So that way they will have the F and the L. Then after that, what they will do is they will take a micrometer screw gauge or a vernier caliper to measure the diameter, and then they find the cross-sectional area. Then they will find the extension once you put in the load, and then they will use this formula FL over AX to find the Young modulus. Now, of course, this is possible, but it will not be very accurate, simply because in physics, whenever you're required to determine a constant, the best way is to plot a graph. So that way we can eliminate both systematic error and also reduce the random error. But if you just do one set of reading, okay, or maybe some people say, okay, let's repeat this reading 2 more times, that means you have 3 sets of readings, well, you will be able to reduce your random error, but you will not be able to reduce or eliminate your systematic error. So how do we do it? Okay, let's examine the equation again. So remember, the equation here is E equals to FL over AX. So we rearrange this equation to make F as a subject. So you get F equals to EAX over L. Now, you notice that if I plot a graph of force versus extension and compare with the equation y equals to mx plus c for a straight line, you notice that since the force is the y-axis, the extension is the x-axis, so the gradient will give me EA over L, and there will be no y-intercept, so therefore it should be a straight line passing through the origin. And if I am able to plot the straight line and find the gradient, I will be able to equate to EA over L, so therefore the Young modulus is the value of the gradient multiplied by the original length divided by the cross-sectional area. So that way we will be able to eliminate systematic error as well as reduce random error, because when you plot all the points and when you draw a line of best fit, you're actually reducing your random error. And if there was a systematic error, it will actually cause your graph to shift. So you notice that originally from the equation it was supposed to be a straight line through the origin, but your graph actually shifted a bit to the right, causing a small x-intercept. But it doesn't matter, because when we calculate the Young modulus, we are only interested in the value of the gradient and not the value of the y-intercept. So therefore we will still be able to calculate the Young modulus accurately. In order to plot the graph, obviously we need multiple values of f and x to be able to plot the points. So what do? Is we use this test wire, all right, and we attach a vernier scale and some load here. So why do we need a vernier scale? Because when you are trying to stretch a wire, the extension is actually very small. It is different if you are using a spring. If you use a spring, the extension is quite significant. But if you're using just a wire, the extension is too small. If you are just going to use a pointer with a ruler. So if you're using a vernier scale, the precision can go up to 0.01 centimeters, compared with just using a pointer, which only gives you 0.05 centimeters. All right. So how do we use this vernier scale to measure the extension? So we need a main scale, because if you remember, even your vernier caliper, you will have a main scale and a vernier scale. So the 0.01 centimeter is by referring to the vernier scale. Here we will use the reference wire to hold the main scale. So some people ask me, is there anything special about the main scale? I would say it's actually the same scale as you would find in your meter rule. So then they ask me, why can't we just use a meter rule? Why can't we just clamp a meter rule here rather than using a reference wire? And you'll notice that there's also a fixed mass to keep the wire taut. Now, the reason is there's another function of the reference wire besides using it to hold the main scale. Now, when there's a fluctuation in temperature, the length of this test wire will also fluctuate. For example, if it gets hotter, it will get longer. But if we are only using a meter rule, which is, let's say, made of wood, then when there's an increase in temperature, the wooden meter rule and the test wire would not extend by the same amount. So you will find that the vernier scale reading here fluctuates. But if both sides are made of identical wires, which means to say the reference wire here, we will use the same material, same original length. Then what will happen is, if there is any change in temperature that causes your test wire to fluctuate, it will also cause the same fluctuation in your reference wire. So that means the main scale and the vernier scale would move together and would not give you any readings. So next, what we will do is we will keep increasing the load here, okay, and every time you increase the load, you would measure the new extension. So you'll be able to get multiple points here, and then we will be able to draw a line of best fit. So in order to measure the cross-sectional area of this wire, we can always use a micrometer, screw gauge, or vernier caliper, and use the formula pi over 4d squared to be able to find the cross-sectional area. Now, if you want a significant extension, don't forget to use a long wire, because a longer wire creates a larger extension. Now we're going to learn about ultimate tensile stress. Now, when you plot a graph of stress versus strain, all right, sometimes you will encounter a graph like this. And the maximum value of the stress here, you'll notice the maximum here is called the ultimate tensile stress. And the point where it breaks, the value of the stress is called the breaking stress. But sometimes if the graph is like this, then you'll notice the highest point is also the point where the material breaks. So then the ultimate tensile stress would be the same as the breaking stress.